these two batteries here are called alkaline batteries. Alkaline batteries are the most common type of single-use batteries. They last relatively long, have high energy density, but they are not rechargeable. This means that the reaction cannot be reversed by turning it back into an electrolytic cell, but that makes it relatively cheap. An alkaline battery is a type of a galvanic cell or voltaic cell because it uses a spontaneous or thermodynamically favorable reaction to produce energy. This means that the Gibbs free energy value is less than zero, and the electrochemical cell potential is greater than zero. This uses a redox reaction, which allows the transfer of electrons to produce electricity. And the reason why it's called an alkaline battery is because there's a basic electrolyte that makes the pH greater than 7. So this is a diagram right here. If we look at the diagram, we can see that the redox reaction happens between the anode and the cathode. And the anode and cathode are separated on purpose so that the reaction does not proceed unless a wire or some sort of conductive material is placed on the outside to connect them. And this is done on purpose because let's say there was no wall separating the two, and the reaction would just happen and the battery would be dead. So this allows the battery to store energy and have the reaction proceed whenever it is needed, but stop whenever it is not needed. If we connect the positive and negative terminals, then the electron can now flow and the redox reaction can occur like this. At the anode, there is zinc metal, which reacts with potassium hydroxide in an electrolyte form, meaning it's aqueous. And this is the basic electrolyte we were talking about. Oxidation always happens at the anode, so the zinc is oxidized and it will lose electrons. The electrons leave the negative terminal where the anode is connected to, and it'll go to the positive. So the electrons go from negative to positive and into the cathode. At the cathode, there's manganese 4 oxide, also called manganese dioxide. Reduction always happens at the cathode. So the manganese dioxide is reduced and gains the electrons coming from the anode. Just a side note, there's often going to be graphite powder mixed in the cathode to help conduct electricity, or in other words, to help the electron transfer to the manganese to help reduce it. Graphite is one of the rare covalent networks that will conduct electricity, and that's super useful because it doesn't easily corrode like most metals, so it's useful in batteries. So let's take a look at the half reactions. Zinc is turned into zinc oxide, and the oxidation state of zinc as a pure metal is 0, and it turns into positive 2. Manganese 4 oxide is turned into manganese 3 oxide. So the oxidation state that I just mentioned is from +4 to +3. So in order to balance the half reactions, we need to first balance them as if they were in acidic solution, and then add hydroxides to turn it into a basic solution. So note that these steps do not actually represent the real steps of the reaction, it's just a strategy to help balance it. First, the manganese is balanced right here, so there are 2 on both sides, and then we add water to balance out the oxygens. And we add hydrogen ions or protons to help balance out the hydrogens that we just have from the water. And then we add hydroxides on both sides to cancel out the hydrogens, because this is actually a basic solution. We combine the hydrogens and hydroxides on both sides to form water as part of our step. Again, this is not the actual reaction. We're just using this to help balance the reaction. And then we can cancel on both sides the water, and we get the final reaction right here. We add the electrons on both sides. So note that there are 2 electrons in both of the half reactions, so we do not need to multiply by any coefficients when applying the full reaction. The oxidation half reaction right here, the zinc reacts with 2 hydroxides to form zinc oxide and water. And the oxidation potential is positive 1.29 volts. But usually you'll see it in another form, which is that the reduction half potential is negative 1.29 volts. In the reduction half reaction, 2 manganese 4 oxides react with water to form manganese 3 oxide and 2 hydroxides. And here, the reduction potential is 0.16 volts. And the overall reaction, we can just add all of these and we get that the cell potential, the total standard cell potential, is positive 1.45 volts, which is approximately equal to 1.5 volts. Of course, this is just the standard cell potential, so it can change depending on a lot of factors, like the purity of the substances, the temperature, etc. So let's take a look at this diagram again. We can see that the battery will eventually die when there is not enough of the reactants, zinc, or manganese dioxide to continue the reaction. In other words, the system will be at equilibrium and the cell potential, or voltage, will be 0. The potassium hydroxide electrolyte is not in the total equation because the hydroxide is being consumed right here and produced in both half reactions. If we look at the diagram, the ion conducting separator allows the hydroxide ions to flow to maintain a balanced charge, so charge doesn't build up. It's kind of like a salt bridge in a concentration cell. But using this process, a machine such as a light bulb or a motor can be put in between the current and it'll be powered by the electricity. 6 1.5 volt batteries can be put together to make the 9 volt battery we saw earlier. And that's it for the alkaline battery. Thanks for watching.